Okay, in the last lecture we successfully derived this expression for the commutator of Lx and Ly. And we found that this is equal to IH cross Lz. And I told you in a similar fashion I can calculate other commutators like Ly, Lz. This will turn out to be IH cross Lx, and I can also calculate Lz Lx and show that it is equal to IH cross Ly. Okay, this is not difficult to remember, it is quite easy to remember. I should also tell you that if you, instead of writing it like this, suppose you had written Ly Lx, what would happen? You would have Ly Lx minus Lx Ly. This will be the definition of Ly Lx if you had written like this, and this obviously is the negative of that. So, therefore, the order in which these things are written is very important, because if you interchange the order, the object actually changes sign. So, one has to be careful. So, we find that Lx does not commute with Ly, neither does Ly commute with Lz. Lz does not commute with Lx, right. It is as if they do not like each other, I mean they do not commute with each other, none of them. But interestingly what happens is that L square, what is L square? This is L square, and I will now show that Lz commutes with this, right. But if Lz commutes with this, what would you expect for Lx and Ly? Well, you see, I mean all directions in space are equivalent. So, therefore, if Lz commutes with L square, you would expect that Lx, I mean what is so special about Lx? See, x, y and z are things that we choose, right. God has, I mean this is our convenience, we have the hydrogen atom, I choose x, y, z, you may choose x, y, z in a different fashion and so on. So, there is really actually no difference between Ly, Lz and Lx in some sense, they all have to be having the same kind of property. So, therefore, if Lz commutes with L square, naturally you would expect that Lx also will commute, not only Lx, Ly also will commute. It is just that they do not commute among themselves, but they are going to commute, this is what you would expect. So, how will I do, how will I show that? Well, it will take a few minutes, but I can prove it. What I want to do is, well, this is vector L square, it is an operator, I forgot to write that hat, but it has to be there. So, therefore, this is actually vector L square. What is going to happen is that you will have Lx square plus Ly square plus Lz square Lz, this is what you would expect. Well, what is going to happen is you will have the whole thing followed by Lz, right. and then LZ followed by the whole thing, correct. But then you can see individually I can write them. You see this is actually nothing but Lx square commutator with Lz, right, plus Ly square commutator with Lz. Very easy to verify this if you want to verify, but I would say this is obvious. This is what it is, correct. All that you need to do is, if you are not convinced, what you do is you write this followed by that, from that you subtract this followed by this expression, and you can see that it is just this object. Now it is not really necessary, to do this, but this is convenient, because see this is Lz square and Lz commutator. Now as far as these things are concerned, you see whether I write Lz square Lz or Lz Lz square, it is all the same, because both of them are equal to Lz to the power of 3, both of them, and therefore what will happen, both of them are equal, which means that the commutator is actually equal to 0. So this term vanishes, and we have to calculate, well there is a square missing here, so let me put that. So we have to calculate these two commutators. So let me calculate the first one, Lx square Lz minus, the first commutator is this, minus Lz Lx square, correct. Now what I am going to do is, you see all that I know regarding Lx, Ly, Lz are summarized here. So I know what these things are, so I have to somehow use these things, that I have to use these things and evaluate that expression which is written there. And how will I do that? A simple trick, you will write this as Lx square Lz minus Lx Lz Lx. I have subtracted a term, I have, of course I have to compensate for my subtraction, so therefore I will add the same term, so that everything is fine, right. This and that will cancel, so I have just introduced a 0 there, and then of course I will have minus Lz Lx square. Now you will see that this is quite useful, because you can now say, okay, Lx square Lz minus Lx Lz Lx. So what is that actually? I can take out an Lx and write the remaining term as Lx Lz minus Lz Lx. Now you see the advantage, because I know exactly what this is, because this is nothing but the commutator of Lx with Lz, right. This object is the commutator of Lx with Lz. And what about the other one? In the other term, you see I can take Lx to the other side. Fine, and this is nothing but Lx commutator of Lx with Lz plus, this again is just the same commutator of Lz with Lx, sorry, Lx with Lz and Lx, this is Z. So what is the commutator of Lx with Lz? We have to make use of this last relationship, but Lx and this is not exactly that, but obviously what I have there, any one of the commutators there is just the negative of this commutator. So therefore, what is the answer? This is going to be equal to Lx, this object is actually minus IH cross Ly, correct? This object is minus IH cross Ly, and again this also is minus IH cross Ly. So that what is the answer that I get? IH minus IH cross is common, I will take it out, minus IH cross Lx Ly plus Ly Lx. So we have calculated only one. We will calculate the other one very quickly. I will do it. Jump to one step because we are familiar with this. And what is this? Actually, you will find that Ly Lz commutator is just IH cross Lx. So this becomes IH cross Ly Lx plus Lx Ly. And therefore, what do you find? We have evaluated this term, we have evaluated that term, and you find that the second term is nothing but negative of the first, and therefore, what will happen? The net answer is 0. And therefore, my claim that L square commutes with Lz is proved. In a similar fashion, if you like, you can easily show that L square commutes with Lx, it also commutes with Ly. So L square commutes with everything, with Lx, Ly and Lz. But the problem is that Lx, Ly, Lz do not commute among themselves. And further, our Hamiltonian, this is something that I have already told you, our Hamiltonian H for the hydrogen atom, it is actually minus H cross square by 2 mu 1 by r square dou by dou r. I am writing the expression that I wrote in the morning once more. Right. Remember, I had written an expression for L square in the morning. Let me write the expression for L square. L square is actually minus H cross square 1 by sin theta dou by dou theta sin theta Remember, I told you that I can express Lx, Ly, Lz in terms of r theta phi. If you did that, this is the expression that you are going to get for L square. And in the Hamiltonian, what happens? You get exactly the same operator sitting there. This operator sits in the Hamiltonian. If you look into the notes or previous lectures, you will find that, and therefore, what I can do is this operator that was sitting there, there is an angle dependent term sitting there, correct, and then of course you have the additional term minus E square by 4 pi epsilon 0 r, which is the potential energy of the system. That is the full structure of the Hamiltonian, and what is sitting here is nothing but this object without the h cross square. That is what is sitting there. Fine. So therefore, what I can do is I can remove this minus h cross square, I can move it to the other side and say that, okay, after all, my Hamiltonian is nothing but L square divided by minus h cross square. That is all, right. Because you see in the Hamiltonian, this portion was the angle dependent term, which is precisely what you find when you actually calculate L square. So you can write it in this fashion, and therefore if you like you can rewrite the Hamiltonian. Maybe I will write it once more. What it tells me is that Hamiltonian is equal to minus h cross square by 2 mu 1 by r square dou by dou r square dou by dou r, that is the kinetic energy term. Actually, if you remember, kinetic energy due to radial motion, something that I have mentioned long ago. This and that together can be written as plus 1 by 2 mu r square. I am combining this with that. There is a minus h cross square here, there is a minus h cross square there, so they will cancel each other and you are going to get L square here, that is occurring in the Hamiltonian, right. This together with that will convert it into that, and then you have minus E square by 4 pi epsilon 0. That is the form of the Hamiltonian, right. And this object, what is it actually? If you think about this, this represents the kinetic energy due to angular motion, because that is the only term that depends upon angles. It does, right. None of the other terms it depends upon the angles. So this actually represents the kinetic energy due to the angular motion, and you can see further that in the Hamiltonian the angles are occurring only here. There is no angle anywhere else, right. So suppose I asked you what is the commutator of H with L square. L square has only angles in it, right. So that L square is going to definitely commute with this part, because this has no angle in it. It is also going to commute with that, and L square will certainly commute with L square. So therefore, what is the conclusion that I have? L square actually commutes with my Hamiltonian, right. And then when you think of Lz, question is, would it commute with the Hamiltonian? Well, the Hamiltonian contains L square, that is the only angle dependent term, and we know that Lz, this is something that I mentioned earlier, we know that Lz will definitely commute with L square. So therefore, Lz also commutes with the Hamiltonian. And as I told you a few minutes ago, there is nothing so special about the z direction. If Lz commutes with the Hamiltonian, then naturally I would expect Lx as well as Ly will commute with the Hamiltonian. Definitely this is something that I would expect to happen. Even though I have not actually done any computations, this is what I would expect. And further, the way we have found the solution of the Schrodinger equation, we solved the Schrodinger equation for the hydrogen atom, and if you look at the equation obeyed by the angle dependent part, right, you would find that, I mean, this operator, you remember where was it? This operator we had written in all its details and then tried to solve the equation, and when we solved it, what did we find? We found that the I am just writing the equations that we had actually encountered. This was the equation for capital theta. If you remember, this is the equation that we solved. Of course, you may say that okay, this was not exactly the way, but there was a beta sitting here, but we found that acceptable solutions will occur only if this beta is equal to L into L plus 1. That is what we find, and therefore I have put instead of beta L into L plus 1. And further, I also know that capital phi obeys this equation. Okay. And the point that I am going to tell you is this: it is possible for me to combine these two equations and get an equation that is actually obeyed by the product. See, you have in the angle dependent part of my hydrogenic wave function, you have the angle dependent part which we denote as YLM. Theta of phi referred to as spherical harmonics, and that was defined to be theta L magnitude of m of small theta capital phi subscript m small phi. This was our definition of Y. So, it is actually possible by using these two equations that are written there, it is actually possible to show, again I will not show it, but fairly simple thing, that if L squared operated upon YLM theta phi, the answer is actually simple, right. If L square operated upon these things, what is going to happen? L square contains this operator, right, and y contains theta, and L square also contains this kind of operator, and y contains phi. So, therefore, these two equations together with these two equations together can be used to find the result of L square operating upon YLM, and you will be able to show that that is nothing but L into L plus 1 H cross square YLM. Not a difficult result to derive, and therefore I am not going to give to derive this, but this is very easy actually. All that you need to do is just use these two equations, you are going to get that. And further, our state function for the hydrogen atom contains, our wave function for the hydrogen atom contains, what was the form of the wave function? Psi n L m. theta phi r theta phi is actually equal to RNL of small r multiplied by y Lm of theta phi. This was our wave function. Now, I know that y Lm satisfies this equation. So, therefore, if I had operated here with L square remember it operates only upon the angles. So, directly it will go and operate upon capital Y, and what would be the result? The result will be nothing but L into L plus 1 h cross square times that function itself. So, why am I saying this? The answer is very simple. If L squared operated upon your eigenfunction psi NLM, what you get? You get psi NLM back, and you get it back, but multiplied by L into L plus 1 into h cross square. So, this actually means that the functions that we have found are eigenfunctions of the operator L square, and therefore, if I am able to measure L square, the answer that I get will be equal to L into L plus 1 into h cross square. This actually means that the magnitude of the angular momentum, right, the magnitude of the angular momentum is such that its square is equal to L into L plus 1 h cross square. And remember, L is a quantum number, it cannot have arbitrary values. So, therefore, and what are the values? The values are actually L equal to 0, 1, 2, 3, etc. So, therefore, you find that the square of the angular momentum vector can have only values of the form L into L plus 1 h cross square with L equal to 0, 1, 2, 3, etc. Or you can say that the length of this vector should be L into L square root of L into L plus 1 into h cross, right. This is the this only possibility, I mean I should not say only possibility, it is square root of L into L plus 1 h cross with L taking the values 0, 1, 2, 3, etc. So, for example, if you are in an s orbital, what will happen? L is 0 and the magnitude of the angular momentum vector would be equal to 0. And if you are in a p orbital which has L equal to 1, then you will have root 2 times h cross, then the next possibility is root 6 h cross, okay, then root 12, etc. First possibility, of course, I should list this 0 times h cross. Now, this is actually somewhat different from what happens, not somewhat, very different from what happens in classical mechanics. Imagine I have the nucleus and the electron is moving around it, let us say in a classical orbit. Classically, say the size of the orbit can be anything, radius can be anything, there is no condition actually. I mean the speed has to adjust. If the radius is large, it can go slow. Well, if the radius is small, it has to go fast, so that it stays in that orbit. Okay. So, therefore, if that is the way it is, the angular momentum vector can have any magnitude. In fact, any magnitude in principle starting from 0 to infinity is possible. Okay. So, therefore, classically speaking, you see there is no quantization of angular momentum, nothing. But quantum mechanics, as we know, is different. It does not allow everything, it allows only certain values for the magnitude of the angular momentum vector, and these are the only values, right. And the states that we have found, the psi and Lm, they have a precise value for the energy, they have a precise value for the square of the angular momentum vector also. Why do they have a precise value? The answer is that L square and the Hamiltonian, they commute. Because they commute, you can have precise values for both, right. And then we are going to look at LZ. Lez, I told you the expression for Lez in terms of Cartesian coordinates. I also told you that if I expressed in terms of polar coordinates, the answer will be minus I h cross dou by dou phi. Right? And if you remember, the object YLM actually contains capital phi, and capital phi, what was the form? Capital phi had the form, I mean I can choose it to be 1 by square root of 2 pi e to the power of I m phi, right. I can choose it to be this with m taking the value 0 plus or minus 1 plus or minus 2 plus or minus 3 etc. There is also another possibility which I did mention. For example, if m is equal to 1 or minus 1, you can say okay, I will have e to the power of plus I phi, I will also have e to the power of minus I phi, but they are complex and therefore we can combine them, and that is the way we obtained our px and py atomic orbitals. We did it right in one of the earlier lectures. But suppose I say this is the function, then I have this very nice feature, allow minus I h cross dou by dou phi to operate upon phi m. What would be the result? This is nothing but the operator Lez. Well, when you differentiate with respect to phi, what happens is that this Im will come down from the exponent, right, and Im will come down, and then that Im and this minus Im will make it into plus mh cross into capital phi. Correct? And what does this mean? This means that this particular function capital phi subscript m is an eigenfunction of Lez, right, because you allow Lez to operate upon phi m, the answer is equal to m h cross times phi m. But then if that is the way it is, I can say okay, Lez suppose it operates upon psi NLM. What is going to happen? You see, the psi NLM depends upon phi only through capital phi, the other parts do not depend upon phi. So, therefore, this is effectively Lez will operate only upon that, and then that will give back capital phi itself, and therefore, what happens, you get mh cross times psi NLM. So, therefore, the eigenfunctions, the way we have found, they are eigenfunctions of Lez also, right. And what does it say? If you measure the value of Lez, the z component of the angular momentum vector, you will get only certain values. You will get only values which are of the form mh cross, right. You do not have any other value. Now, this again is quite different from what happens in classical mechanics. You see, in classical mechanics, if I have an angular momentum vector, okay, let us say this is the angular momentum vector. As I told you, in classical mechanics, the angular momentum vector can have any length. There is absolutely no problem, any length is allowed. Why? Because the particle may be moving slowly or may be moving fast, depending upon which the angular momentum vector can have any magnitude, right. And not only that, this vector, you see, it can be oriented in any direction in space. There is no condition on the way it is oriented. Therefore, its a z component, if you think, it may be having a value 0, maybe, or maybe the z component is positive, or maybe the z component is negative. It all depends upon how this vector is oriented in space, right. And all it can be oriented in any direction. So, therefore, the z component of the angular momentum in classical mechanics can have any value. But here, what is it that we find? We find that first of all, the length of the angular momentum vector can have only certain values, right. And not only that, its z component is constrained to have only certain values which are of the form m h cross. So, let us look at a specific example. Let us say that I have L equal to 1. If L is equal to 1, actually I am thinking of a state that we will normally refer to as P. It is the p orbital that we are thinking of. L is equal to 1, and for such a state, what is the value of the angular momentum vector? You will say, okay, it is nothing but square root of 1 into 1 plus 1 h cross. So, this is the value of the angular momentum vector, the length. Okay. So, if I say I can say this is my origin, and then I will draw an angular momentum vector like this, such that the length is actually root 2 times h cross. Now, if L is equal to 1, I know that m can have 3 values, 0, plus or minus 1. These are the 3 possible values. And if you think of physical significance of this, I have told you the physical significance. M actually specifies the z component of the angular momentum vector. So, for example, if you say m is equal to 0, that means the z component of the angular momentum vector is actually 0 times h cross, right. And how will I represent that? Maybe I can draw a line like this. This is my angular momentum vector. Length is root 2 times h cross. It is oriented in this in such a fashion that it is perpendicular to the z direction. This is my z direction. And if my angular momentum vector is oriented perpendicular to the z axis, then naturally its z component is going to be 0, which is what I want. So, therefore, if you say L is equal to 1 and m is equal to 0, that just means that the angular momentum vector is oriented in a direction that is perpendicular to the z axis. What are the other possibilities? M is equal to plus 1 means that the angular momentum vector is oriented in such a fashion that its z component is plus h cross. So, what does that mean? It just means that this angle is such that the projection of this vector on the z axis is equal to h cross, correct. And if you say m is equal to minus 1, what does it mean? This is actually meaning that it is pointed downwards such that the z component of the angular momentum vector is now minus h cross. So, therefore, if you think about it, you see what it says is that the 3 states that I have for L equal to 1, I have 3 different possible states characterized by different values of m, right. And what are they different in? They are having the same value for the length of the angular momentum vector, correct. And therefore, if you thought of kinetic energy for angular motion, they will have precisely the same value, because the length of the angular momentum vector is the same. So, now that means kinetic energy has to be the same, and therefore, why you see why the total energy of all these systems, all these states are the same. If you remember, these are degenerate states, right. That is because you see the kinetic energy for angular motion is the same for all the 3 states. And what are they different in? They are different in the fact that the angular momentum vector is oriented in different directions in space. That is all. There is no other difference from the other, I mean qualitatively speaking, that is the main difference. Then the other thing that you have to understand is that, you see, if I drew a picture like this picture actually says that, well, this is my, let me say, my y axis, this is my z axis, and the way things are drawn, this is my x axis. Okay, this is my x axis. If I drew such a figure, actually it means that the value of Ly, I know precisely what it is. That is what it means if I drew such a vector. But then I know that Ly and Lz, they do not commute, and therefore they cannot simultaneously have precise values. So, if you have specified the value of Lz, that means the value of Ly should be uncertain. It is not tied, I cannot specify exactly what its value will be, right. So, therefore, here actually what happens is that the value of Ly can be anything, and therefore, you can only specify the value of Lz, you can also specify the length of the vector. Unfortunately, it is not possible to specify the value of Ly, neither is it possible to specify the value of Lx. You cannot. Why? Because the operators are not commuting. If they commuted, there will not be any problem, but they are not commuting. And therefore, what can you say then? Well, you can say that I have only these two things known. One, length of the vector, two, its z component, right. And therefore, I am forced to now say that, okay, the angular momentum vector can be oriented in any direction along the surface of such a cone. All that I can say is that this interior angle of the cone must be such that the z component of the angular momentum has a value plus h cross. That is all that I can say. I cannot say anything more. I cannot say anything about Lx and Ly, right, because they are uncertain. And similarly, in this case, I cannot say that this vector is lying in the zy plane, but I will have to say that it is oriented somewhere along the surface of such a cone, and the orientation is such that the cone is such that the z component of the angular momentum vector is minus h cross. Now, in the third case, in this case, right, in this case again I can say, well, the angular momentum vector is in the xy plane, but in which direction, that I cannot say. So, it may be oriented in any direction along the surface, along the periphery of a circle of that radius. So, the condition actually that the z component of the angular momentum can have only values which are of the form mh cross. This is usually referred to as a space quantization of the angular momentum vector. Now, this is for, well, I realize this figure is not very nice. So, the different orientations are shown in this picture. Similarly, if you like, you can worry about other states. If with L equal to 2, suppose you had L equal to 2, what will happen? It is quite simple. If L is equal to 2, let me draw another figure very quickly. Length of the angular momentum vector will be root 6 times h cross. If L is equal to 2, the values of m can be 0, plus or minus 1, plus or minus 2, 5 different values. So, I would have 5 different orientations. So, let me draw the first one, the second one, the third one, fourth and fifth, right. This is actually how much, 2h cross, 1h cross, 0h cross, minus 1h cross, and finally minus 2h cross. Unfortunately, the way I have drawn this does not appear to be, I mean it is not, the scale is not correct actually, but I am sure you can understand. So, this is how the orientation could be. Five different orientations. Okay, I think I will stop here and continue later. Thank you for listening.